Question 1 says, what phenomenon occurs around a wire when an electric current flows through it? Yep, that is a magnetic field. When you have a wire and current flows through it, the wire generates a magnetic field. And we use what we call the right-hand grip rule to find out the direction of the magnetic field. That's that about that. Question 2 says that the magnetic field lines around a straight current carrying wire are best described as concentric circles. So in that case, you tend to have the wire like this, and then the magnetic fields, they go round and round and round like that with the arrows. 3 says the direction of the magnetic field around a current carrying wire is determined using what we call the right-hand rule. 4 says when using the right-hand rule for a straight wire, your thumb points in the direction of the electric current. Yeah, so when you do the right-hand grip rule like this, your thumb points in the direction of the current, your fingers will curl in the direction of the magnetic field. Yeah, that is question 5. You've already answered that from the explanation. The strength of the magnetic field around a wire depends on what exactly? Well, that is the size of the current and the distance from the wire. The bigger the current, or let's say the larger the current, the larger the magnetic field. And then the closer the field is to the wire, the stronger it is. The fields will spread out like the diagram we drew here. So if we extend this now, the magnetic field is weaker here because it's at a farther distance from the wire. And here the magnetic field is much stronger. 7. A bigger current in a wire produces what? Well, it produces a stronger magnetic field. We just said that. As you move further away from a current carrying wire, the magnetic field becomes weaker. We explained that already. A solenoid is essentially a coil of wire. Now, for a straight line wire, the magnetic field isn't that strong. But if you want to make the magnetic field much stronger, you can take that single wire and then coil and coil and coil and coil and coil and coil. So the wire will give you a strength, or the strength of multiple wires. So in this case, it's as if you have many different wires. So the magnetic field you get will be much stronger. And in actual fact, it's just one wire that you've turned. And then for the records, the higher the number of turns of the wire, the stronger the magnetic field. So keep that in mind. Number 10, the magnetic field produced by a solenoid is similar to that produced by a bar magnet. Yeah, because the magnetic field goes like this and like this, like this, like that, like that, like that. And then you have your direction. So this guy behaves like a bar magnet. So the diagram of the field is just the same as a bar magnet. So the magnetic field lines goes in and out. 11. Inside a solenoid, the magnetic field is typically described as what? Well, it's uniform and very strong, because you have in the solenoid, just the same as the bar magnet, you have the magnetic fields. Uniform. That's a uniform magnetic field. And then once it goes out of the solenoid, it curves. So you get the perspective of the question. 12 says, what characteristic describes the spacing of magnetic field lines inside a solenoid? That is equally spaced. 13. Increasing the current flowing through a solenoid will do what? Well, it will increase its magnetic field strength. So for a solenoid, you want to make the magnetic field strength stronger. All you have to do, increase the number of turns or increase the current. Those are the two options. 14, which is the last question. What can be placed in the center of a solenoid to significantly increase its magnetic field strength? Yeah, that's a block of iron. If you place a block of iron right here, you're literally turning this from a solenoid to an electromagnet. So that will be all for this video. I'll see you in the next one.